So we just wait for each sibling created by active parallel pragma to finish preceding statement before proceeding to the next statement. Okay, so we have now an explicit wait. So far, our parallel construct, basically said that we'd start off threads here, and when the construct ends, threads finish. Now, and at that point, the parent thread is waiting implicitly. Now we have actually a form of waiting, which is called a barrier. Okay. Questions? So this is a very important construct barrier. Yeah.
So I got an iterative question. So
iterative question?
So why did you choose to only have 2 threads in the model instead of having
5 threads, 10 threads? Yeah. So we are going to address that question maybe next time. Okay?
Okay.
So we're going to deal a lot with that. But what's the intuitive answer? How many?
Be a balance between resource costs of creating threads and the efficiency gain from having more threads.
Oh, so that's of course there. But when we have zillions of entries, yeah, if we have a loop is going to go for 2 iterations, having 2 threads is just ridiculous. Right. Okay, so obviously the cost is higher. You want the cost to be amortized. So the larger the loop, the more threads you want. And then I'm going to discuss the issue about how to utilize the processors properly too. So that becomes an OS issue, and I do want to address that.
I would say it depends a certain amount, like how many threads you want, depends a certain amount on the limitation the CPU is placing on the
So there are all these iterations. Right now I'm trying to just figure out the constructs, and we're going to look in some depth at that issue. Okay, and I was making the slides this morning, so I'm hoping we'll finish the stuff next time. Okay, but I do want to cover all these issues that come around. I don't want to just leave this topic in between. Okay, so let's go and see what other declarative constructs we can have. So now let's go back to Robert's question. This thread number business is not nice. So now our goal is to get rid of thread number. What construct can you imagine to get rid of this thread number here, to do this problem? Imagine a declarative construct. Round with process iteration, we'll get rid of later. Let's just get rid of, that also has thread number in it. But what about this other part? Yeah.
Why not have something like OMP thread 1 or OMP thread 0? Something like that.
Okay. So I can do that. But going back to, so we will basically have OMP before instead of if, we'll have OMP thread 0. And instead of else, we'll have OMP thread 1. Excellent. Excellent and not excellent, yeah.
Okay, so right now it's getting the whole list and it's only executing on it if it is a certain thread number, right?
We're just trying to divide the work among 2 threads.
Right, well that's what I'm saying. I was wondering maybe you can get rid of the if you just only give the thread the chunk of the list that it's supposed to work on.
No, this is not the chunk part. This is the part that you either do a sum or do a 2 text.
This is the second part. Where first we did the initial calculation, now this is the printing. So this is just asking one of the threads to do first and the second thread to do the other one.
Okay, this is just that. But can anybody, and I said this is a great solution, it's not a great solution. So why is it not, it is declarative. Why is this not a great solution? Going back to the previous question. Yeah.
So I'm confused what the OMP barrier actually does here.
Okay, somebody want to explain what OMP barrier does?
No, I mean why isn't your if statement enough?
No. The barrier is for the line.
The barrier is for the ROM processes, so I have
it's not.
Oh, great. Right.
Yeah.
So if you want to get rid of the imperative construct, you have to pass the statement to.
So you're not passing, remember, because we're not defining a runtime method. We are just, but yeah, in essence we are passing, but it's really that we annotating statement. So he's saying let's have the annotation be thread 0, thread 1. And I like it and I don't like it.
There are ways to split it up. I could see one possible problem. Thread 0 and thread 1 might be busy at the time.
So you might. So how many threads are you thinking we have at this point? Because there's a barrier. We know that this is preceding a barrier.
Yeah.
Succeeding a barrier.
Okay.
So we know all threads are free at this point.
I see. No, I was thinking more generally. I was thinking without a value.
Okay, good, good. But you're kind of getting to the problem I'm trying to
Like,
point out.
why do I have to say thread 0 thread 1? Can't I just say point it to different threads?
A thread, another thread.
A thread or another thread,
Or,
whichever you want to.
and if I have 5 threads, or if I have 1 thread, so supposing, so I'd like this code to be as unaware of what happened earlier as possible. So for instance, the number of threads could be something that can be set by an environment variable when the program is run. Okay?
Can you schedule it to just the next available thread?
So what if I had only 1 thread? Yes.
Schedule it to use the next available thread. Just wait till you get the next available free thread and then point it to that free thread.
If thread scheduling is, I don't know how OMP is handling the processing, but if we think of like things to be handled by threads as a stack, just push them onto the metaphorical stack.
Yeah.
And then just however many threads you have available, have them always consume from that stack. I assume OMP would have a way to do that.
Just queue the job onto a queue, and every time a new thread is created, it will just pull it from the queue.
Right. Okay. So,
That's like a task pool.
sorry?
A task pool.
So this is exactly a task pool. This, you guys are getting it. That you're basically saying these 2 statements can be done in any order. Each statement is executed by only 1 thread. Unlike our parallel construct, where each statement was executed by all threads. So this is, I should have put this slide here. You know, have you guys have heard the term multicast? So you know there's unicast. What could multicast mean? So unicast is send a, go ahead, go ahead.
So I think multicast was one thing. It's
So unicast is when you send a message to only one process. Multicast is when you send the message to multiple processes. Anycast is when you send the message to any one of a set of processes. Okay? So if you've got some work to be done, you say here's a pool of slaves around and send the message to any one of them. So this is like anycast. Okay? Where you're saying send this job to any thread, and if there's only 1 thread, make the thread do all the tasks. Otherwise, divide it among the threads. If there's 5 threads, only 2 threads do the task, the other 3 threads don't do anything. Okay? So this is the syntax. You are saying this is, we're going to divide it into OMP sections, and then we're going to delineate the different parts by OMP section, and we assume in sections, by the way, this is very important. I was Googling for sections to see how they work, and the first question is in Stack Overflow, where the guy's sections construct is not working because he did not put a parallel before the sections. Sections assumes that threads have already been created and is dividing the work among the threads. You can go and say OMP sections parallel in one line, which means say create the threads also and do sections. Okay? So that is actually the number 1 thing that comes up. So that's, yeah.
So if you have, so you still have 2 threads and you add like a 3rd section that does some other task, will it do the first 2 and then the first one that finishes will do the 3rd one?
Something, that's left to OMP scheduler.
Okay. Yeah.
So this is exactly what Sam was saying, that we basically have a task pool. Okay? And we are saying that these tasks can be done in any order. Okay, and this is very interesting because in imperative languages, there's often state. You can't have one section go and change a variable that is referenced by the other section and expect it to work in that order. So this kind of construct is more useful when you do stateless programming. Okay, functional programming is particularly, remember we talked at some time of eager evaluation, and they just suggested that, look, why not, I said, what could an eager evaluation be? And they just said, why not have all parameters of a function evaluated in parallel, okay, rather than left to right, which is what most languages assume. And you can do that in functional languages if there's no state. If the evaluation of one parameter doesn't change the state that is referenced by another parameter. Okay, yeah, you had a question, Raja?
Yeah, so just a syntactical question. So if I have like multiple statements in a section, do I need to put that in a curly bracket, or can I just leave it one after the other?
So right now you see I've gone and put OMP section here, I haven't put a curly brace here. But in general, OMP section or any of these things take a statement as the expected statement. They annotate a statement. The statement can be a atomic statement or a block.
Okay.
But yeah, the implementation, by the way, is a bit fragile. So I had to work around with it.
Yeah. No, I was just curious, like, does this work like a case statement or does this work like a if statement basically? So like in select case, it goes one after the other regardless of block or not.
Yeah, this is the whole idea. There's no order here.
Yeah.
So it is not like case where you expect things to go in an order.
No. I'm talking about within a particular section. Semantically, like if I have let's say in one section I want to put a trace and then I want to do a print line. My question is, will that work even without a block?
No. You need to go and put those two statements within a block.
I see. Okay.
Because it's going to take that stuff and put it in a runnable. And it has to delineate that.
So it seems like the semantics for OMP are based on plurality, where if something is supposed to be like reading multiple lines, then has a block, but if it's not supposed to be reading multiple lines, it doesn't have a block. Is that true?
So, the way you want to look at it is that a statement can be an atomic statement or a compound statement.
Sure.
That's the way you want to look at it. And these annotations annotate statements. That's it.
So they're not blocked if they're an atomic statement, and they are blocked if they're a composite statement?
A composite statement is a block.
Yeah.
So, I don't know what the confusion here is. It's got to be a statement.
So like we can't debug. Like a statement like this, your IDE is not going to tell you, hey, your annotation is supposed to be in a block. So I'm trying to make sure that I can like read this and understand.
Yeah, you have to, so you can, a lot of things can go wrong here. Remember that an annotation is a statement. That statement can be an atomic statement or a block statement. That's it. That's the rule. It's not just an OpenMP. Your for loop body has to be a statement. It can be an atomic statement or compound statement. That's just programming languages.
So what happens like in the sections block?
If you did what he said,
Yeah, if you have a statement.
if you have statement after that, I try to look and look and look, and you better not do it. I have a feeling that that statement will just be ignored in the implementation. I try to see what will they do if you mix sections with non-section. In fact, why do you even need OMP section? Why can't you just say the next n section statements are that? And I try to figure this out, and my best bet is that this is designed for Fortran, and Fortran doesn't have compound statements. So it just went and said that this is our way of doing. So in Fortran, I believe it will just go and take the text between OMP sections, because the Fortran I learned, Fortran just keeps changing. In fact, they used to say that we don't know what the language in 2025 will be, but it'll be called Fortran. Okay, but it was very line oriented. So in that case, it will not work. But otherwise, yeah, Sam.
Doesn't the OpenP section give you the flexibility to put a block as opposed to just saying it's a list of statements? Like it itself could take a block. So for example, if you want to summon and print at the same time, you could you could hand a block to OpenP section, not just a.
So that's a composite, though. I thought you.
No, that's what I'm trying to tell you, that we could have had semantics. I don't know why you guys think of block and statement separate. They're just statements. I don't know what you're confused
I'm
about.
just saying the reason that in an OMP section you have to do a list for each thing is because you could also argue that you want one thread to work on two methods, right?
Yeah, so you put those two things in a block.
Yeah.
So Ken's question is, what if I go and put another method here, another statement here? What are the semantics of that? It's not, these two are not in it's an orphan kind of thing. And I cannot see, I looked at tutorials on this, I looked at the documentation, and they just don't ever even allow for that case. Yeah.
Can you put like curly braces and put a bunch of statements?
Yeah, that's what a block is. Okay.
So that's.
Yeah.
So, but if we have a block, it's no longer atomic. So I thought you said OMP section is supposed to be atomic.
No, I said it's a statement. It's a statement. I never said it's atomic. A statement can be atomic statement or a block statement.
So we're allowed to have a composite statement on OMP section?
Yeah.
Yeah, of course.
The thing is that they should not interact with each other because that creates dependency issues.
Yeah, it's just a statement. I mean, you have,
Okay, so it can't be a block, but it has to be a statement, not a block. What?
a block is a statement.
A block is a
Okay, I just tried to.
when I teach 110, I always give the syntax, the grammar of it. For loop is for something statement. A statement can be, and that's what, if, you guys even did my recursive descent parsing, where we sort of saw that, expression can be, a sub-expression is also an expression. I mean, you can take two sub-expressions, combine them together, still an expression. Okay. So here's a better way to visualize this. Okay. So when I learned programming, my first language was Fortran. My second language was Pascal. And we had begin and ends, which is what your curly braces are in C-inspired languages. Okay, so normally we have begin, end. This is a block. Okay, now we have a block with a bunch of statements, and the semantics are that each statement is executed in sequence by the same thread. Okay, so this is sequential construct. And co-begin, co-end says that the statements can be executed in any order by different threads. Okay, and anybody want to guess when this construct got invented? The co-begin this is not my words. It's words of a great computer scientist.
I'm going to say COBOL.
No, this was not in COBOL, but it was invented by a very great computer scientist, whose name I think you would have heard if you've done algorithms at least. But anyway, you want to guess which decade it was invented in? 60s. Good, that's a good guess. Okay, so a statement section is executed by single rather than all threads, and co-begin can replace begin. And heard of Dijkstra?
Yeah.
Okay. Sorry?
It's graph algorithm.
Yeah, he's done a lot of things. So even when I was an engineer in India doing EE, I had a book called The Discipline of Programming by Dijkstra. I've yet to read it, but I was very proud to have that book. Okay. So just remember though that co-begin, I believe, was parallel with sections. And this is just what we have in OMP is separate parallel and separate sections. There's no confusion there. And I was reading up, there was a big debate between whether you should have fork join or co-begin, co-end. And so I didn't look into the deep. I think you should have both. But there was some debate about which is better or which is sufficient. Okay, now we are getting into more depth here. How about we go and, I have to correct this too. So there should be a process iteration here too, which I deleted accidentally. But we have the interface, we have this implementation. We can imagine having a factory method that goes and chooses among them, and that's all fine. But I'd like to really get rid of this from the programmer. And is there any hope that you could get rid of this from the programmer? You can't get rid of this from the programmer if what process iteration is doing is application specific. Is what we're doing here in any way specific to round? No. Right? It's just taking loop parameters, taking so we can imagine the process iteration being a bit built into the language. Right? So, and suppose that the programmer says, hey, I don't really care. OpenMP, you choose. Okay? Then what declarative construct might you imagine?
Constructor.
Sorry?
I feel like it's going to be something like a constructor. If we're not setting an arbitrary value, it's going to take the default value.
Yeah, but there's some code here. You've got to go and we've got constructs. What are the constructs we have so far? Parallel, barrier, sections. Process iteration will be associated with what kind of statement? It has to. We want to have some annotation associated with the statement. It'll be associated with what kind of statement?
Parallelized iteration or something?
Sorry?
Parallel iteration or something?
Parallel iteration is what we want to happen. But somebody wrote code that didn't even know about concurrency. And that code would be what kind of construct?
For loop.
A for loop. Okay? So we want to add something to a for loop to say that, hey, divide the iterations among threads automatically.
Something like OMP section or spawn or something?
Something like that. Okay? So we have this OMP parallel thread num. Can OMP automatically implement process iteration and call it based on loop pragma?
So like using this operation, if we go back to the rounding and summing example, why don't we have like, well, if you're going to write this in a single for loop to round and sum the numbers, you could iterate through the array like NJ was saying earlier. First you round and then you add it to the sum. Why don't we do a process like that using this process iteration?
Okay, I don't know what the relevance is what you said to what I'm saying. Let me just clarify the question I'm trying to answer here. How do I get to the process iteration declaratively? Okay? And we just decided we needed some thing associated with the for loop. Okay? This is what we have. I want to get rid of process iteration. So my specific question is, we can answer, you may have some orthogonal question which we can answer later. I want to just finish this thread. How would you like me to change my annotations to go and say, get rid of process iteration, hey, OMP, you do it yourself?
Could you just ask OMP to do some like split?
Something, okay? Where would I add that split?
Wouldn't you,
Where would I, I'm fine, where would I add it here?
wouldn't you replace just the if statement?
Okay, you will put it inside the loop,
In your annotation, just add it as another parameter.
just add another parameter in the annotation as long as what we've got is a for loop. Okay?
Why not just ignore it if it's not a for loop? It's like if you
That's what it'll do.
say someone accidentally puts it as a parameter.
Hopefully that's what it'll do.
Yeah.
You know, but this is very dangerous.
Hopefully it's because
Yeah, hopefully it'll do. I'm telling you, I gave, I mean, you don't know what the implementations are. I gave this implement. I don't want to criticize this poor undergrad who did this implementation, but I gave it a program without any OpenMP pragma in it at all. And it just gave me a an exception. And I had no idea why it was giving me that exception. So, you know, if the rules are not, in all your implementations in general, I say, remember in 401, if there's an error, don't worry about it. Okay, just assume that the input is correct, because handling all the error correction cases just takes a lot of time. And let me tell you, this is because I am not a security researcher. A security researcher will never accept that. Say, let's get the errors right and the functionality later. So a lot of the security researchers just said, don't add functionality, literally. There were people, security researchers, who were telling Bill Gates, why do you keep adding features? They create security holes. And Bill Gates said, because users want them. You know, so there's always this tension that those who, you know, anyway, nothing ventured, nothing lost, right? So this is it. You just say OpenMP for thread num, okay? And this should really be put with for loops, and if it's not, you know, who knows what will happen. Okay?
Seems overly simplistic, but okay.
Okay, it is, and we'll go and find out problems with this. But at least, remember what is the principle in systems design? Make the usual case easy and allow for the unusual case. Okay? And remember, this OpenMP is being taught literally in 110 classes. Yes, when they teach loops, they go and say, we can do it in parallel too. That is the goal of a lot of people. So when I went to this conference, that's what they were doing. And I said, hey, if they're doing this so they want 110 to be taught with whatever is relevant to 110, 401 to be taught with that. And think about this. We have this one class on distributed systems. You have algorithms, data structures, programming in the small, programming in the large. All of these can be preceded with the adjective distributed or parallel. And we have to go and bundle all of these things into this one class and make judgment things. Why not add it to all? And again, I've gone to NSF panels where they say security should be taught in every class. Why have a security class at the end? Okay, so there's this viewpoint.
So, counter argument aren't all.
There's always there's always counter arguments. Yeah.
Like in every single philosophy class, every other book is relevant. So, like my confusion for this one is, so do you actually mean OMP, the thing an undergrad created, is being taught to other students?
Sorry?
Do you literally mean that OMP is being taught to other students?
It's being taught in 110 like classes. I'll give you 10 papers which.
UNC undergrad wrote OMP.
No, why are you so obsessed with what's happening in the UNC? We're talking at abstract level here. Why are you concerned with UNC students?
The thing I'm trying to get at is like, what is the enterprise
Why do you care?
Because I'm curious.
That's not an issue. That's not the scope of this. Okay, OMP is available outside too. OMP can be done there. I'm just talking at an abstract level. This is what we do in academic classes. Okay, and there are places that go and teach this to 110 students. As simple as that. But this is something, given that I saw the Stack Overflow question, this is something that people do use in the enterprise. And the reason was that it is the right hammer to use sometimes. Okay, I don't recommend this to do your assignment 1 in it. Okay, but certainly you can do this with in certain problems. Okay. Okay. So conceptually, OpenMP calls process iterations, but you really don't want every thread to go in to have this if statement. So this is just, just think that there's a process iteration. Really, you can have a thread pool, you can have lots of other things going on underneath, but conceptually, it's divided among all of these things. So can we allow this pragma to be associated with every loop? That's kind of what Chris was asking. And if we go and say, again, I should go and correct this. If we go and put this OMP parallel for in this for loop, who knows what's going to happen? But it certainly won't know what to do because it doesn't have the loop parameters. It doesn't have I, step size. Okay. Okay. Questions? So OMP for parallelism needs counter control loops. Have you guys ever heard the term counter control loops? Counter control loops as opposed to what else? Have you ever heard in your 110 like classes? Dissection of loops? So when I teach 110, I divide things into counter control loops and event-based loops. And does that intuitively make sense?
Yeah.
Sorry? For loop, but in Pascal there was for and while. In C, while became for became both for and while. You can do anything, but basically, you have to know how many iterations it will be done at the start of for loop. Okay, and so event is that while the loop is executing, the termination condition can be known at that time dynamically, not at the start of the loop. Okay, so allow different iterations of a counter control loop to execute in parallel based on properties of counter control loops. Okay, so we've been able to do a loop on an array with our round. And now let's go and sort of try to address,
How do you enforce that in Java and in a language where for and while loops are the same thing?
How do you enforce that?
Yeah, how do you enforce a counter-controlled loop when you'd have to understand I don't understand how procedurally you can tell, okay, this is a counter-control loop, even if it's a for loop, it may not actually be a counter.
No, think about it. Think about it, guys. So what do you think OpenMP implementation does with the for when it sees a for? Sorry?
Takes each part of the expression and tells you what to do with it.
So there's, for is first part, second part, third part. So it'll have to check, what is the first thing it'll have to check? Does it have all three parts? Right? And it'll assume that the first part declares the variable, assumes the second part is the terminating condition. I always keep forgetting which way it goes. And the third part is so which way does it go? Yeah, third part is the increment, right?
Yeah.
So,
Even with those three parts, I create a while.
you can do, if you do something tricky inside, like breakout or change the variable, if that's a variable, supposing the limit is a variable, and you go and change that variable inside the loop. What will OpenMP do? Crash, or OpenMP will just store the initial value it had, the variable had. Okay?
So OpenMP basically overrides and restores it, is what you're saying?
It will override and things will just go haywire because you might go and put a break statement there. So from what I've heard of people who've used OpenMP, like OpenMP is used in 633. 633 is a class? All kinds of problems occur if you're not careful. That's why you better be careful. And that's why it's better to teach it to 110 like students. who don't even know how to do all these things than to people like you who will do nasty things with the loops, right? Put break statements in.
So OpenMP basically forces your code structures to go very simplistic.
Well, let's just say it's regular. Remember, the usual case should be easy. Okay, and when you're doing these computations, by the way, they all have very simple loops. We'll see what map reduced to. It's a very simple loop. Okay. So now let's get into Gatti's thing. He said it's too simplistic. He didn't like it. Anybody want to guess that why you should have control over process iteration? Why not let's just OpenMP deal with it, whatever it does?
Maybe one part of the process iteration depends on the previous parts.
But then you wouldn't use process.
Yeah, then you better have no. Oh, that's the other thing. Your loops better not have dependencies. For instance, this is the kind of problem that really occurs. That even occurs in 110 like that your I plus first iteration shouldn't depend on what was done in the ith iteration or any other iteration. You really, sorry? You can imagine that to be a side effect. Okay? But let's go and see this. So let's go and see how we could do this. And one is Gatti's approach, that I've got 4 elements here. I've got 2 threads. And Nichar, I keep seeing you staring at Chris's computer. What's going on there? Okay, try to go and not look there.
Yeah, NJ, mind your own business.
Very good question. Very good advice. Yeah. If that is an inspiring thing, I should take a picture of that laptop and put it here on the exam day, so that you guys can all focus on it, and have your.
I'm discussing what routes need to be taken down in the Rams rock climbing gym.
Thank you for telling me that you're not paying attention. No wonder I see the questions that come out from you.
Yeah, it's going to be a real thing, is my last question.
Right, because that you can ask without regard to what I've said before, right? You can just interject anything you want to without relevance. It's something you can do in concurrently. There's no serial execution there. So but that is something. If you do things like that, becomes disruptive. Okay, if you really want to pay attention somewhere else, then just at least don't disrupt the class with questions of that kind. Okay. Okay. So, okay. So what is the way you suggested we?
Have one.
So that's
thread.
one thread did this. The other thread that was
rounding. The other one.
No. Let's just focus on what you said originally. Okay, that was the alternate direction. So float twist round does the first element, then the other one. Nurture.
I'm thinking about why.
I have to keep watching you now.
I have the habit.
Now that I know what's on the screen.
It's a lock screen.
I have a habit of looking in
Okay, good.
direction I am.
Okay, so we've got this, we've got here, we've got this. Okay, now tell me, that's one approach. Another approach is I keep the distance as far away as possible. That we've got the first guy do this, then we try to divide it evenly. We take the other thread and make it do something that's as far away from that element as possible, and so forth.
Wait, how is A2 the farthest? Isn't it?
We want to divide this into 2 sections, right?
Oh.
So I'm basically saying, I'm going to assume that we're doing top to bottom. So I'm just trying to keep the sections as far away as possible. Okay, but I will do them top to bottom. And in one case, they're treading on each other's toes almost.
Is what you're doing here starting on 2 ends, and
You can think of it that
or
way.
are you starting at the
Right.
and halfway boom?
Right. So
Which way is that? Which way are you trying to illustrate?
I'm illustrating the point that I'm separating these guys. Think of it as 2 threads starting from 2 ends.
Okay.
If it's 2 threads,
Yeah.
if it's 3 threads, we'll have to go and I'm just saying we are breaking it up into as big a section as possible and keeping them as far apart as possible. So in one case, I'm keeping them close to each other, in the other part, I'm keeping them far apart.
So this is like a scheduler problem, like how are you going to schedule the different things that's going to happen, in which order are you going to schedule them? Like, not exactly schedule, maybe schedule.
Okay, this is more like a memory access issue.
Yeah, yeah.
It's not a scheduling issue.
Scheduling is not.
We have decided that we are going to have 2 threads.
Yeah.
We are going to go and schedule them in any way we feel like. And I'm going back to my Indian roots and just following how he's pronouncing it. I'll go back to my American roots later and say schedule. So, we'll go and so it's not a scheduling issue.
Yeah, no.
It's a memory access issue.
I'm using schedule as a not.
So let's look at memory accesses. Do I want to keep the memory accesses close to each other or far from each other?
Close.
Further from each other. For safety of data.
Sorry?
Yes. To prevent.
I'm not concerned about safety here. What I'm saying is that if I'm going to access memory, and the memory does not exist 2 places, even if there are 2 threads, if I access the memory using 1 thread, by principle of locality, the area around that is probably going to be in some cache somewhere. So I want to access the area close to it so that I can speed up my computation.
So this is important. There is a cache.
Sorry.
Okay, so let's talk of locality here. So he's describing locality, which is very good. So locality argument is that that processes typically tend to access data structures close to each other. So so what they're going to access should be kept close to each other. So based on locality argument, do you want the closest distance approach or the furthest distance approach?
It depends how many threads are going to access.
Okay, let's assume that in this example, okay, but we'll consider we'll let the memory block size and the disk block size of everything be whatever I want to be. Okay, but in this example, do you want it to be closest or furthest with 2 threads? We'll go to n threads. The same arguments will apply to n.
For the distance between the divisions, or the
Yeah.
distance between.
So do we want the ones where they're going right, the elements of access by 2 different threads are right next to each other? Or do we want them to be as far away? And far away could mean I could have zillion items here.
As far.
As far?
Otherwise,
Okay, one at a time, guys. Let's give Hunter a chance. Yes.
Okay, I said farthest because that way each thread's accessing stuff near it and not overlapping with the other one. They're near either.
Okay, so that's important. So if they keep them far away, they're accessing data structures far away in memory, so they're not near each other. And why is that good?
Because the area is nearest to them or what's relevant to them, not the other one. They don't want to overlap.
Why should they not overlap?
Because they're doing different stuff.
Sorry?
Different stuff, different data is what they're putting out. They don't want to overwrite each other.
They're not going to override each other. In both the cases, they were looking at different items in the array. Just remember that. In one case is that the different items are close to each other. In the other case, the different items are far from each other. Okay? So we haven't quite figured this out. This question is complicated. So we're not going to answer this very easily. Okay, Nishad, what is your argument?
Going into a deeper level of locality here.
Let's go and answer the question I'm asking. Let's not, okay, close or far? We'll go into your question later. Close?
Yeah.
You want to keep them right next to each other. Why?
Because if, as you said, there are billions of zillions of amounts of data,
Yeah.
I don't want to page fault every time.
So if there's billions of data and one of the threads is doing the access, we got its page in memory. We don't want to, and supposing there's only one page that we can have in memory at all, just extreme case. If they're far apart, then we're constantly page faulting each time the new thread gets access. Sorry?
Oh, I can say that's cool.
So page fault is the following. So I'll show you in graphic detail. Okay? But and it's not going to be bad. It's going to be good. Okay, Sam?
We only spent 2 weeks on it less, I think 5:30 less. That's
Okay, we won't. Okay. Let's keep on going, guys. Sam, you had something.
Well, like, if you can only keep, say, 2 of those in memory at a time, if A0 and A1 are in memory at the same time, then both threads can access what they need to actually work.
That's what Nish's argument is, right?
Yeah.
So we want to keep them close to each other.
Exactly.
There's also these arguments of safety. As long as we program this correctly, which is a big if, there is no safety concerns. As long as
Yeah, no, you know, if you don't program this correctly, you know, especially with this pre-compiler, open Java case, you can't even debug the code. So you better just pray that it works, okay? But in C, you can. And again, if this was something that the Java compiler would, the reason why you can't debug this is because the debugger is not integrated with the implementation. If the debugger was integrated, it could do it. It's not again the poor undergrad's fault, okay?
So as long as like your page table itself is randomized, there's not much issues of data.
No, what he's saying is that, you know, if you keep them far apart, the chance of errors manifesting themselves are smaller.
No, that wasn't what I was saying. I was saying that there shouldn't be any difference.
Logically, there's no difference. The only thing is this mysterious page faults that we might get.
My argument that it might be better for them to be further apart wouldn't work if you only can keep one.
Okay, but
same.
give me an argument.
But my thought is that if they're close together and one of them is accessing a certain area of memory, you could lock that certain area of memory, and the other thread will have to wait to get, let's say, A0 and A3 are in the same part of memory, and thread 1 locks that.
I just love what you just said.
Then the thread 2 will have to wait for it to release in order to.
So
check
if
it.
the areas are too small next to each other, maybe there's some locking going on, which Gatti is saying, and there is. And we might just come up with
Did you
interference.
say there's only one page?
Sorry?
Didn't you earlier posit that there's only one page?
And
No.
I acknowledge that if there's one
No.
page, then it's.
Yeah. So
things you write.
I want the answer to be, always the answer is in between, okay? And we've looked at one extreme case, and since I have only 4 items here, you know, I assumed one page, but when you have more items, the same page issue can arise. So let's look at Gatti's thing. Why would you lock, by the way? The answer is perfectly correct, I love it, but why would you lock an area around memory? As long as 2 particular threads are accessing different words in memory, why would you lock an area around memory?
In the case that some other row thing wants to access the same word.
No, so you were good till that time. Now you're not good.
All right.
Yeah.
I'll just stop. I'm just taking this case. If we use an atomic instruction, it locks the bus port. So, even though we're trying to only lock one bit of memory, the actual implementation is locking the whole line. So,
The whole what?
yeah.
Yeah, so that we want to make sure that the memory to register transfer is as little as possible. And again, these talks that we've been seeing in faculty candidates, they're all trying to fasten things up by doing everything with not going to memory, having something called data flow computation, which is kind of what this task is. In this task, you're first rounding up the value and then splitting it up and then combining. So that is a separate kind of issue. But let's go. Anybody else know why we might just lock some area of memory? This is very subtle. I don't expect you guys to know, but that's a very good intuition you had. So here's what's happening. Okay, there is disk, there's memory, and there is processor cache. This is what everybody hadn't considered so far, and the cache is where we're going to get into locking issues.
No, I talked about the cache.
Sorry?
I talked about the cache.
Okay, but we haven't considered that in our answers. Okay? And the cache is where this locking issue is going to come about. Okay? So let's say our disk, Hunter, has only 8 elements. Okay? And our memory has only 4 elements that it can have. Disk is always bigger than memory. Right? Can we ever have a program that processes 8 elements if our memory can have only 4 elements in it?
Maybe use the cache and memory.
So hang on. So can we write a program that processes 8 elements, given that a memory can fit only 4 elements at a time? Yeah. How would you do it?
Instead of using cache and memory somehow,
What?
take my date.
Even if you didn't have a cache,
For it to be in the cache, it has to be in the memory. Cache is like
Yeah. Yeah, you can't just add those things up. Because then,
It's because you can change things in memory.
you can swap things, and that is pitch point.
Otherwise, the cache is not going to be up to date with
It's
what's
both things
actually
with
there.
other elements.
so what you do in your screen? His screen first had all this stuff he was doing, and now it is blank, and now soon it'll have my notes, right? So that one screen can only fit how much data?
A screen's worth?
But you can keep swapping. That's called swapping, that you can use something, you can load something first, then, so you can, there's something called working set where you can only operate at one time on only this part of this part. So as long as you can work on one element at a time, or two elements at a time, or four elements at a time, you can indeed do this, okay?
So you work on, if you have memory, 4 things in it. You work on 4, you swap them out for 4.
So you swap something in, swap something out.
Okay.
When he goes and puts my notes in,
Last 4 you swap.
sorry?
So you can only work with 4 at a time. So
Yeah.
you lose the last 4
But you can store information about that 4 somewhere.
on the disk.
On compute, on memory too,
Okay, yeah.
okay? So that's what happens.
Well, wait, how would you store the old 4 if you can only store 4?
No, but you can store some summary of what you did with the 4.
Oh, okay. Like there's just a result.
Because you did something with the 4, right?
So a working set is a subset of the memory, and like a certain part of the memory will have the mapping.
So the term working set is how much you hear in common language, right? My working memory, this is what I'm doing. Just as in scheduler, you have the processor sometimes going and doing this thread, sometimes doing this thread, is switching between the threads. So the memory is switching between different parts. Okay? And cache now is what?
It's on a processor.
Sorry?
It's on a processor.
It's the processor and
Quickest reference to the memory.
so it's even quicker.
Yeah, 411.
That's what's in his head, hopefully. Okay? That's what's gone from the screen to his head. And that's the cache. And and I keep telling you guys before your exam, please reload your cache. Okay? And so because you want fast access. In my exams you had a lot of time, but that's typically what exam preparation means, that you put it in your cache.
Just a quick clarification, since you're dealing with page table swapping, I'm guessing this is the LRU cache.
What cache?
LRU cache.
So what policies are used for this is orthogonal to what we're going to talk about. And by the way, the term working set was invented in Purdue. In fact, Purdue became very, very famous by a guy called Denning. And he did a lot of analysis on what is the best policy. And, he used the word LRU, which says that, when you have to swap something in, there are many candidates to remove. So which do you remove? There's all kinds of policies possible. And, in data mining, you're always sort of looking at previous data to answer new questions. To me, this whole memory management is a form of data mining that got invented in the 60s or 70s, I don't know when Denning was working, where it basically said that we look at past accesses to predict future accesses. Okay? So that's something I won't get into, because I don't want to spend, how long did you guys spend on memory management? 2 weeks? So hopefully
Memory management was like before.
Okay. So now let's go and see. Hunter, I want you to understand this properly, okay? T1 wants to access A0. What's going to happen?
It's going to bring you
So the region around A0 through,
A,
I guess A3 is going to be put into the memory, and then it's going to be loaded into processor cache, depending on what it takes.
okay? Hunter? You were noting down. Don't draw. I've got this picture here. Please pay attention. This is all for your benefit.
T1 wants to access A0, so it goes to the memory and then goes to the cache.
Yeah, so it went to memory, then to cache. And this is where you're going to access it. Got it?
Are the P's referring to processors?
Processors. Processors.
Processors.
So the threads of it, okay? And your whole locking thing is going to come in because we have multiple processors.
Does the order of processor and thread mean anything?
No, why would it mean? This is just attached.
I don't know if this graphic has more meaning to it.
It's attached. It's attached, okay? So, but that is the problem with graphics. People, let's say, by the way, are we out of time? Okay. Okay. So let's just finish this picture and then we'll continue on. Next.
I remember page faulting by 6 days.
So, okay, yeah, this is the model that you have now. Now, let's say P2 accesses A0. Okay? And so it's going to access A0 here, right?
No.
And do you see a problem?
It's locked.
Every time I do some change to A0, it has to ping pong to the other cache.
So we need now, you guys have been doing this two-phase commit and you've been doing atomic broadcast because you have replicas of values. I have replicas of the same value in two different places. If they are at the same value, if they happen to be the same cache line, this is the cache line. If they're both accessing the same cache line, the concurrency control is done not at the word level, but at the cache line level. Okay? So this is an example of true sharing conflict, and we need to run some kind of algorithm to make sure that they don't make conflicting changes to the same value. As long as they access the same cache block or cache line. Okay? In this case, this is a true sharing conflict. They both happen to be accessing the same word, so it's a true sharing conflict.
Is this not a case for doing the furthest division?
That's what I'm saying. So, this is the case for doing the furthest division.
I was right.
Okay, and he was right too. Okay, sometimes you're right for the wrong reasons. So now we go and look at the closest division approach. That was a bad thing what I did. Now I did something. The consistency is maintained at the cache block level. The bit is this, just as you have granularity, that certain things are done at the page level, dirty bit is kept at the page level, not at the word level. Concurrency is done at the cache line level. So now I'm doing the close approach, and P1 is accessing A0, P2 is accessing A1, but the system thinks there's a concurrency control problem and it does this thing. And the overhead is larger. So you want to keep it not too far apart and not too close. So that's the point. Okay? Yeah.
What about, so maybe I hope this isn't a convoluted question. What about something like a data structure that is like contiguous? What if you have processors that are accessing multiple parts of the array, so they can't actually be far apart? How does this apply to something like that?
So we get into trouble there. So I'm just saying that when we have control here we know that the iterations are independent.
So is this a method for how to separate data on a disk?
No, this is a method for separating the iterations among threads, assuming the iterations are independent of each other.
So
In a very constrained environment that a for loop is doing, so in a very constrained environment, we are saying that we want to make sure that they don't overlap. Okay?
The generic idea is that two CPU caches should try to have different data. If they have same data, one update will make the CPU update every other CPU's cache, and we do not want
Let's just go and let's not get into the exact algorithm used, but think of two-phase commit. Okay? And just imagine that when they're the same thing, they have to run this algorithm so things get slowed down, and we are trying to make things fast. Yeah. Okay. This will be on recording.
Enters right.
Okay, good. And hopefully what Nirjal said was recorded, but you do want to make sure that when there are two processors that are working on data, they don't have the same data in the cache line, otherwise you're just going to run this algorithm. And I can't tell you how many talks I've seen on various kinds of cache coherence algorithms. There's zillions of them, but there is a cost with each of them. So just better to, when you can, keep your data far away. Okay? So we look at the furthest distance division. Let's take 2 more minutes. Okay, so T2 accesses A4. Okay, and this is for you, Hunter. Now what's going to happen?
Goes to the cache.
No, goes to memory first. It goes to memory first, and then goes to, so you get these page faults. Okay? As you shuttle between various data.
Page fault because memory was overridden.
Yeah, because they're far away. So you can either keep T1's data in memory or T2's data in memory.
So the cache loss was had because
The cache lost, even memory lost.
Okay.
Okay. So we'll continue from here next.
Wait, why is the cache?
Hunter, for your benefit, I have added some text on how paging works. Okay. I've tried to reduce as much as possible jargon that you don't need, such as virtual memory or virtual address space. But that should be enough for you to get some idea, because we want to focus on the issues that are relevant to OpenMP. So this is the memory access model. I've got the text here so that you guys can read this and study for it in the exam. And then we talked about cache conflicts. Also, that if your two processes are trying to write two words that are right next to each other, then you get false sharing, and then you have to run a consistency algorithm, which is costly. So the moral was that if we have to go and split work among different processes, different threads, we want to make sure that the threads aren't accessing memory that's too far away, because then you might end up with page faults if you really have very large amounts of data compared to your memory. And if we do it too close and they are writing, then we can get into cache conflicts, and that will cause performance problems. Okay, so that's what we did last time. And the question the reason we talked about this was, we had to address the question about how should iterations be automatically divided among threads. And Gary said, look, doing it completely automatically is too simplistic, and we've figured out it was too simplistic. Okay, we needed some flexibility. So we still don't want to write our own process iteration that decides for each iteration where to go, but we'd like to have some loop parameters that go and allow us to give us some flexibility. Okay, and the parameter we're going to have is a step parameter. It tells you how many consecutive iterations should be done by one thread. Okay, so if we set it to, and we look at the numbers soon, so we can set it to any number, and that says that these are the number of consecutive iterations that a process should do. So if, for instance, if I have 7 iterations in my loop, 8 iterations, 7, right? Yeah. 7 iterations in the loop, and I say my step size is 5. Okay. Then and T1 gets allocated first. Which iterations will T1 get allocated? 1 to 5, right? And whatever's left will be given to T2. Okay. So this is bad load balancing. Okay. Besides the fact that if you make the step size very large, we might end up with threads that are too far apart and cause page faults, and we can also end up with bad load balancing. Okay, so we can go the extreme and say that step size is 1. Okay, so we alternate. Okay, and now we have better load balancing. We are just off by 1. Okay, and does this ever make sense given that we have cache conflicts? Possible cache conflicts. If we have step size of 1, are we guaranteed the kind of conflicts we talked about last time? Remember that if two threads are writing to adjacent memory cells, okay, then there'll also be adjacent memory cells in a cache block. And if both of them are loaded the cache blocks, then we have a cache coherence protocol that has to be executed. So if we set the step size to 1, are we guaranteed to have a cache coherence protocol on each access?
No, if you let your data such that everything's on a separate cache line,
No,
then
but they will. If you're doing it this way, they will be on the same cache lines.
because if your data,
If we are doing it I1, I2, I3, I4, you're pretty much guaranteed they'll be in the same cache line.
Shouldn't you want a step size that ensures that?
Before we go to what we should have, I'm saying, does this step size force a cache coherence protocol? I'm trying to hint that no, even if they're the same. I'm trying to hint that it is not. The answer is no. The cache coherence protocol is needed when 2 threads writing, and we can have threads just reading the values. Okay, if I'm summing up an array, then we are not going to write to the array, we're just summing up the array. Okay, so this does make sense. A lot of the problems, in fact, I took the round problem, which is not classic. You don't see that as an example when you read up OpenMP. The classic example is summing up a set of values, which we're going to talk about soon, which is also the harder problem. Okay, so is this ever reasonable given that they can be false sharing and adjacent reads do not conflict? Okay, writes conflict. This is very important. Okay, questions? Okay, so going back to what Gatti was trying to hint, that we really want to sort of compromise step size. So we might choose 2, for instance, rather than the extremes of 1 and 5, and we give 2 here, 2 here, 2 here, here, and then we have some. In this case, we still have a little bit of load balancing, but not as bad as we had when we had 5. Okay, so based on your data size, okay, we can try to go and choose a proper step size to have a good compromise between locality and load balancing. Okay.
Wouldn't you want the size for your schedule to be big enough so you wouldn't have the page fault?
That's right. So you can do all that. So this is the choice you have. You don't want it to page fault. We don't want it very, very large. And if you have it very large, then also the load balancing problem becomes an issue. We don't want it too small. Okay. If we are writing. Okay. So let's talk about load balancing. Are we really guaranteed load balancing if we evenly divide the iterations?
Not necessarily, because some of the iterations might be more expensive than others.
Some iterations may be more expensive than others. Okay. So you see a word here, static. I never kind of described what static meant, but and so let's go to an example here. My I1 iteration is bigger than I2 and the rest. Okay. So we see here that T1 gets assigned I1 and I2, T2, I2, and at this point, when T2 finishes I4, T1 is still busy, right? Yet we are going to assign I5 and I6 to T1 and I7 to T2. Okay? So there was information there based on how iterations got completed that could have allowed T2 to take some of T1's work, but we statically decided how to go and divide the iterations. So the alternative is dynamic, right? So now we understand why we used the word static before. So what I'm showing you here are attributes that we assign with a for loop. Okay, I talked about attributes to be assigned to general code. This is for loops, and for loops you can go and say this is a for, and that's all we said so far, for and parallel. Okay, and now we can go and say schedule. And we can say static or dynamic. So that's one parameter, which can either be static or dynamic. And the second parameter is a step, which is an int. And then I've got here what the step means. So step means that each thread is assigned a step number of consecutive iterations in static and dynamic. In both cases, that's the number I will do. But in static, you assign all iterations at the start of loop. In dynamic, you look at the load and decide based on that. Okay. So let's go and look at a dynamic schedule example here. So we assign I1 and I2 here, I3, I4 here. At this point, when T2 finishes, I5, I6, and I7 are up for grabs. We know we will assign 2 at a time, but we don't decide where we will assign. So this I5 and I6 go here, and when T1 finishes, I7 goes here. Okay. Questions? So we understand this. Now, dynamic is more flexible. It gives you more load balancing. Why not always use dynamic?
You could think of a software architecture where you intend on the JSON iterations being executed at the same time. If there's some sort of sequential importance of having certain ones executed for others, you might not want it to be dynamic.
No, you better not have that. If you have the sequential dependency, you're just lost. Okay, you can't divide the iterations. But you're saying in some cases static might make more sense because we know that they're all of fixed size, let's say, right? So, but dynamic is more flexible, right?
You have the extra overhead of running a scheduler in order to turn where instead of
So when you immediately know, you don't have to make any decisions at runtime. That's true. But that decision takes a little flag, right? Just looks at queues. That's an if statement. So it's got to be a little more tricky. But you're right. You're on the right track.
It's just not some sort of switching and checking. You have a some sort of synchronization for accessing the list.
Is that what you were going to say too?
Yeah, so I was thinking you have to manage the dynamic processing requires more steps. So
It requires more steps, it requires an if statement, but what we really want to prevent as much as possible in concurrency is synchronization. Okay? So in static, there's no load balancing. And if you don't have multiple threads, then you're switching between threads. Okay? And so there's some context switch overhead after each segment. Okay, so after each chunk, I should say, I used the word segment here, but they really talk the word chunk. Chunk is a set of consecutive iterations you do. Okay, so dynamic, there's load balancing, but after each chunk, you must check a shared data structure leading to synchronization of possible context switch too.
Would there be a problem that happens in dynamic if you have some sort of program that's just tallying? So there's no sequential importance, but you're going through a set of data and you're tallying the numbers, for example, or
Yeah,
categories into another set of data.
Right, our round example was like that. It was just going in, okay, so fine. So you're tallying.
If we go back to I1.
I'm not going to go back because I'm going to lose my recording.
So I1 takes the space of two other instructions,
Right.
two other I's. But if we let it go for 3, and I5 comes in and it needs to tally something to where I1 is tallying, isn't there going to be a problem there?
What kind of problem? I'm not really sure what you're talking about, but
Because you're writing to a section that I1 is reserved.
we just remember these loop iterations are independent. If they're not independent, you're just in deep trouble in static, dynamic, all kinds of scheduling. So that's why I wasn't, let's not look at the problem. You just have to look at the amount of work. Okay, let's not assume there's any dependency among iterations.
So
And
ignore problems for now.
assume for now that the iterations are parallelizable. Okay, that means they're independent of each other. Okay, and we're going to come to some, which is kind of in between, and we'll see a way to fix that. Yeah.
I still don't understand the synchronization thing. What's
So if in static, we go and decide that you do this work, and we can write independent threads that never have to talk to each other or talk to a common data structure because their work is assigned at the start of the loop. At the start of the loop, you know which iterations each thread will execute. In dynamic, after you finish a chunk of the thing, you have to figure out what is the next chunk you will execute. What you will do next depends on what other threads have done. So some shared data structure has to be accessed, like a queue of work. Okay? That means that you have to go and synchronize.
Just like which segment of the array you have to decide.
Exactly. This is not array specific. This is actually iteration specific. You have to figure out which I's or which iteration you're going to access. Okay, so the point is there is some coordination needed after each segment, whereas in the first case, I can at the very start go and say, these are the indices you have to do, and you just go through the indices queue in a private data structure and say, I'm going 1 to 5, now I'm doing 15 to 20, now I'm doing this to this, and all of that can be given in a private a bounded buffer to you. Not a bounded buffer, just a private queue to you. And now you need a bounded buffer like data structure. Okay? Plus you have to do the checking, and you have to maintain this data structure. So if static suffices, use the more efficient case. Okay?
So, how do we evaluate the time complexity of the overhead and the synchronization?
So, in all of these things, if you're talking of big O, they ignore constants.
But it's still important to manage this because it could matter.
So this is performance that in the average case would matter. and you can go and talk of time complexity in terms of the number of threads, okay, and then it becomes order of n, okay, when n is the number of threads. But normally you talk of time complexity in terms of the size of the data, okay, and so this is just overhead, and average performance is something that we don't take care of in big O. But I'm glad you're asking such questions, because and that's the kind of stuff that you will actually do in Jan Prince's course. When you do parallelization, you'll be looking at this a little bit more formally. Okay. Okay, let's see whether we understand this properly. So far, we've had only 2 threads. Let's go and assume there are 3 threads. So I1 and I2 go here because we've got a step size of 2. I3, I4, I5, I6, I7, I8, I9, I10, right? And now, I1 and I12 will be assigned to T3, right? But we could have had T3 do I11 and T1 do I12, and that might have been better load balancing. Okay, maybe in this picture it doesn't show properly, but assume that T1 and T3 finish at the same time. Because the chunk size was 2, I11 and I12 so let me see what I have in text. T2 does, okay, sorry, let me go back, if I had more data. So T2, so I'll take back what I was saying. When T3 finishes I12, and when T1 finishes I8, T2 has yet to finish I9, right? And it'll still do I10, because we decided on a static step size. Our policy is dynamic,
Dynamic step size.
but our step size is static.
Why not have a dynamic number of threads, a dynamic number of steps, and run it dynamic?
Yeah, so the number of threads.
Is this too much to ask for?
So let's do one step at a time. But that is, I mean, that's the kind of flexibility you get with Java.
I wasn't joking. It's like
Yeah, no. Neither am I. I'm not answering your question. Okay, so that's the kind of flexibility you get with Java with your own queue management. So we are trying to remember to declaratively, do the normal case efficiently, allow the abnormal case if possible. Okay, so we're doing one thing at a time. I won't say step. Okay, and the number of threads we'll still fix, because that gets way too complicated. Okay, there are too many variables. Okay, but we should allow maybe the number of steps to vary. And then the question becomes, how do they vary? Give some kind of specification. And the problem here was, so we can, let's see. So a solution could be that we just have a very small chunk size, okay, step or chunk size. But then the dynamic overhead kills us, right? Because, but small steps are used to load balancing. So how about a variable step size? As threads get out of sync, let's reduce the step size gradually. Okay? And so that's called guided. Okay, it should be dynamic square or dynamic plus plus, but it's called guided. Okay? And that also, guided also takes as an argument a step size, but that step size is the smallest step size you ever want the guided to go to. We don't go and specify the range of step sizes. We just say, hey system, do whatever you want to do, but don't make the step size smaller than this. Okay? And it'll choose a large step size first, that it's up to it, and then it'll gradually reduce it as work progresses. Okay, and we've got an example to show exactly what happens, but
I mean, you kind of touched on it, but I was thinking if it makes sense to reduce step size, does it also make sense sometimes to increase step size?
I don't think so, because as things get out of sync, things will get out of sync later, right? In the beginning, they're all at the same time. But I like the duality.
Get them back into sync. Let's say you're like 1/3 of the way done. Why not increase step size?
You could, okay, so that's good. That you decrease and then increase back. That'll be good. And that can be your paper. Okay? So you can go and check that out. No, actually that's an excellent idea. So, and I hadn't thought of it, so that really is good. So chunk size decreases down, and I'm telling you what I've looked at, because you're saying only one, it could do what you're saying also without violating the principle that you'll never go below one. It could increase and decrease. But from what I've understood, they say, how do we decide? The chunk size decreases dynamically, and it is proportional to the number of remaining iterations divided by number of threads. Okay? So let's assume that that's equal to rather than proportional. Okay? So in the beginning, there are 12 iterations. Number of threads is 3. So 12 by 3 is our chunk size or step size, right? So T1 is going to be allocated first. It gets allocated 4 threads. Okay. Now we've got 8 iterations left. Still have 3 threads. Okay, that's how the number is decreasing. The number of iterations reduces, but the number of threads remains constant. So we'll assign the ceiling of this number, and we assign 3 here. Now we've got 5 left, so we assign 2. Okay. Now we've got 3 left, we assign 1, and now we'll never go below 1. So we keep just doing that, and it load balances. But I believe guided will allow what you said also, because that's the word guided. It's just, it's providing its own guide. So, but this is what I've read, based on what I've read, I'm telling you this. Okay? Okay. So, in theory, number of iterations can vary. In practice, can you think of a problem? In theory, iteration cost can vary. In practice, can you think of a problem?
Yeah, so I was immediately thinking, what if like the first n number of iterations are actually the most expensive ones, and then the last ones aren't that bad? You might have accidentally allocated like the 4 most expensive that will take way longer than the remaining 8.
Right, exactly. But finally, the dynamic will allow things to get balanced. Remember.
But so can it take an iteration that's already given to a thread? So in the last example, we gave the first 4 to the first thread. What if those were significantly larger than the other 8? So the other 8 are given to the next 2, then we still have to wait for T1 to finish because it was already given those iterations.
Yeah, once it's been given.
Yeah.
So this, you can consider all kinds of cases here, right? And that is scheduling is a big deal, and you ask Jim Anderson and company, they do a lot of work in that. Yeah. So most of them are NP hard problems. It's a bin packing problem. It's like packing stuff in your, you guys, in your suitcase. It's just an impossible problem. Okay, Hunter, and then.
My question was based on what Chris was saying, right? So the iteration size being larger for some of them, instead of just dividing it up statically, is there a reason it would be dumb to do this if there was an implementation where it was given iterations one at a time, and as soon as it finished, it was passed a new one?
But that's step size of 1.
Okay.
So that's when the overhead thing is a problem.
Well, why? So that's
when
overhead is the reason you don't do that all the time.
And also, if you're both writing, you have fault sharing.
Okay. So yes, I was wondering if that would come back to bite me.
My thought is, since sequence isn't an issue, why not have your list of instructions to do be almost like a priority queue, where the tasks that take the longest are at the beginning, so that your step size is sort of smaller.
Okay. Let's.
First one.
So you should really. I guess you won't be, but take Jim Anderson's course, because they assume you know the step size, the time to execute something. But given the halting problem, can I go and predict before I do an iteration how long it will take? So that's the problem. Okay, and people in real-time scheduling just assume somehow that you can figure that out, and that's how they allocate things. But in real-time scheduling, they do that. They go and say, this is how long my task will take. They tell the operating system. And then the operating system schedules based on how long you think that will take. So that's complicated. This is stuff, like I said, to be taught
Lower level?
as low as 110 level in some places, right? Okay, now, But in theory, we're talking of all these applications. In practice, can you think of some applications where the iterations are of different cost?
Yeah, so I'm thinking of like minimum spanning trees, like the distance between nodes in a network differentiates. So if you're doing computing, maybe you're trying to figure out the propagation delay between nodes. So I feel like every example that has different parameters will have different cost variations.
Okay, so spanning tree is a general technique that can be used for many problems. So you have to figure out what the problem is. But let's take the grading example, which we all know. What are we parallelizing? Assignments or checks? And do they take varying amount of time? Okay. So there's a whole class of algorithms, and they happen in science quite a bit, called irregular algorithms, where these things happen, where the number of iterations varies. And the first time I heard of this was when I heard Jan Prince talk about his research. So he's like a world expert in irregular algorithms. So that's the class of algorithms that have this irregular kind of behavior, and which motivate scheduling policies like this.
So this is kind of a loose connection, but TCP, right, as a protocol, like dynamically allocates whether it'll send more or less in a window.
Yeah.
Kind of related to this? It's kind of irregular.
Not quite.
The exact same thing.
Not quite. Okay. The number of steps remains the same.
Dynamic windows.
Okay. But it is related in the following sense, that you're saying that the network's past behavior is a predictor of its future behavior. And we'll go and do and it has a cold start and a warm, it drops very quickly. And it starts very gradually up, increasing the window size. That's just a heuristic. It's more data mining. And in some sense, this is also predicting, but this is really saying that, look, when I get out of sync, I expect to get out of sync as the competition progresses, I'll reduce, okay? So initially, I might just divide the thing evenly among the threads, and then as threads, and hope that the threads just finish at the same time. And if they don't, then we'll do. So this is what's called a heuristic. It's a guess that things will work out. You just hope it'll work out, and then the way you evaluate heuristics is you take a bunch of data and say, look, my heuristic is better than your heuristic. And a lot of natural language research happens today that way. That's why they have like hundreds of papers in a conference saying, hey, given this data set, my heuristic worked better. And then somebody says, my heuristic worked even better. Okay? And so this is an AI term, which is an erudite term for saying I just guessed, or it's my hunch. Okay? Because there's just so many variables. And you can't prove things because of the halting problem, because of the NP-complete scheduling problems. Okay, we took a relatively easy problem where each iteration was independent. We were just rounding up each element of the array independently. Okay? There was no synchronization cost in the loop, and we could really do this guided dynamic and so forth policy. So threads write to different locations. How about this now? I'm computing the sum of an array. And this is the classic problem that OpenMP addresses. Almost every OpenMP tutorial will go and talk of the sum problem. They'll start with this almost. First the hello world problem of parallel, and then go to this problem. So I've gradually kind of gone to here. Okay, they won't talk about cache lines and page faults. Okay, that's something we've done because we want to look at it from an implementation point of view. Also, they won't go and see how we can map it to a thread in Java. Okay. So what's the problem here? This is going to work?
Yeah, the accumulation isn't going to be atomic, and even if so you might have be losing updates.
You might be losing updates because that's not an atomic instruction. Okay, but OpenMP gives us a way. I can go and say OMP critical. It'll work now. And it'll work. Slower. Right, so now this is the problem we're going to address for the next 45 minutes probably. Okay.
So why can't you make it a subproblem thing? Because like for summing values, you can sum a portion of it, and another portion of it, and another portion of it, and then sum those. Is that what we're going to do? Yeah. Great, okay. We can see this. 45 minutes now.
No, we still spent 45 minutes.
Next
Okay.
45.
Okay? But what you're doing is, what you said was, let us take a problem and use divide and conquer, right?
Yep.
Let's break it into 3 sub-problems, do them, and then combine the results. Or let's reduce the problem to a bunch of sub-problems, and then look at the results of those sub-problems and reduce it to computing the final sum.
So
Okay.
can you like merge sort some this problem?
So let's just say that, let's go and just say that we want to use the abstract idea of reduction. Okay, divide and conquer. Okay, who knows what problem we're going to have to do here? Sum is just one of these examples. We could have to do multiply. We could have to find minimum value of an array, maximum value of an array. Who knows what the problem is? But we want some general technique. Okay, and so reduction, divide and conquer. And for a loop, we'll talk of doing it in 2 steps, which is exactly what Chris said. We'll break it up into 2 sets or multiple sets. For each thread, we'll have a separate sequence that is summed, and each thread then does a partial reduction of its argument. So it goes and takes its sequence and produces a value. So that's a reduction step. It took a bunch of values and reduced it to something. And then we'll do a final reduction in the last step. Okay, the partial reductions can be done in parallel. The final reduction you can also recursively do in parallel. But we are talking of, how many threads? Okay, it'll be proportional number of processors you have. Okay, so we're not talking of billions of threads. Okay, so OpenMP doesn't tell you how the final reduction is done. I mean, it doesn't require you to specify anything, so it could do that in parallel too. But if it does it serially, it's not doing too badly. Okay? So this is what will happen. We can have A1 be processed simultaneously by 2 threads. And so we want to compute some value into the final sum variable. For each thread, we will create a private variable. We have 2 threads. We have sum1 and sum2. Okay? They'll read these values in parallel and add it to sum1. Sum1 was initially 0. They added A1 to it. Okay? And then they will go and add to sum1 the next 2 values in parallel. Now they're all done, and we can go and sequentially add these 2 values to sum. And we could potentially do it in parallel.
Didn't we say earlier that it's dangerous to access areas of memory that are next to each other?
Very good. That's why it's going to take 45 minutes. Okay? I'm very glad that you... Yeah. So good. See, isn't it great when your screen actually is not showing you something distracting, how much your brain can work?
I'm still texting, but I got you.
You have to admit that, right? Okay, partial reduction. So partial solution of problem, reducing it. So reduce sum is in private variable of thread. Okay. Final reduction. Result computed from thread-specific private variables by 1 or more threads. And typically 1 thread. So this is actually a very interesting thing, that sometimes you can solve an atomicity problem by replicating the variable. Okay, so we had one variable sum that we had to compute. We replicated it, but not the variable, but not its value. The values are being computed separately, but we made multiple copies of the variable so that threads can access it independently. Each thread has a copy of it. And so this allows weight-free, lockless coordination. And go ahead.
Sorry, but that word reducible, what do you mean by that, like, exactly? Do you mean, like, in the MapReduce sense, like when you're saying partial reduction?
In the reducible sense that Chris mentioned, that, this...
We're reducing it into parts.
To parts, yeah. But MapReduce is also an example of reduce. So my whole goal of sort of making this reduce a maybe 45-minute thing, maybe it's not going to be 45 minutes, okay, is to sort of show the connection between the 2 reduces. In both cases, we are reducing the problem. Reduction is a general technique of divide and conquer. Yeah.
Are you done?
Not quite. So I want to go and say that lockless coordination is a term, and this idea I saw first in a talk that Jim Anderson gave long time ago on distributed computing. He was using this idea, and I'd never seen it before. I thought it was fantastic. And he was at that time the distributed systems guy. He's actually teaching distributed computing this semester, so he's still the distributed systems guy in terms of teaching at least. And guess who was a real-time guy at that time? Kevin Jaffe. Okay? And Jim was looking for another area in which he could apply this weight-free idea. And guess where there are constraints? Real-time computing. So he started learning and teaching himself real-time computing because he had this cool idea of lockless coordination. He didn't invent this idea. I'm just saying that he had. I asked him, "Did you invent this idea?" He said, "No, I was just using it and I was building on it." So this is actually this is when I first heard of this term of having the idea of replicating things. Okay, but you had this question, Jeff.
What do you mean by replicating it but not its value?
So what did I do? Remember, in your assignments, we replicate the data structure, right? We have to every time we make a change to data structure, it's mirrored in all the other things.
Right.
So we first replicated the simulation, if you will. Then we replicated the changes.
Right.
Here we took someone, which was a type int, created a copy of the variable, also of type int. But every change to one doesn't cause a change to the other one. Only at the end we'll go and sum them up.
So it's because they're separate, that's why. Yeah. So the different threads aren't accessing each other's sums. So
Right.
That's why it's
This is my term for it. People don't use these terms. Okay, so maybe it's confusing, but that was the goal.
No, that kind of answered the thing I was thinking. Does it matter if the sum isn't computed in real time? So like while we're doing sum 1 and sum 2, sum doesn't actually equal sum 1 and sum 2?
Oh yeah, sum does not.
Is that consequential?
No, because we look at the sum at the end of the for loop.
Right. So that's what I was thinking earlier by the replicate a reducible shared variable, is that we have multiple components of sum that are each being computed separately. And then once they're each done, then we compute sum. Is that
Yeah. But the end of the for loop, you're guaranteed. Sum will. So there's something called a post-condition. Sorry?
What if it halts?
What if it halts? Of course. Then, what if lots of things happen? But that's a good point. That what if you accidentally break out of it?
So for this, I can't think of the right term, but for this context to work, we have to have the variable declaration in scope with this method, right?
Yes.
Can't be grabbing it
So I'm right now all figures. Who knows what the code is? Okay? This is all sort of hand-waving right now in some sense. Okay? But by the way, could we have done this with a two-string also? Where we have to find a two-string of a whole array?
So it's not as nice in Java, but you can do this. So it's like strings are immutable, but we can still concatenate final strings.
I want two-string of the whole array.
But the ordering.
Ordering matters. Okay?
So what about sequential access of memory? We split the memory down into however many threads we have, and then thread A, thread B, thread C get executed back, concatenated into the final string.
Yeah, you'll have to go and impose some order there. You'll have to, we are doing this in parallel. What do the iterations get done? That thread 1 gets A1 and A3 and thread 2 gets A2 and A4.
Why not make the steps the number of threads you have?
Yeah, once you use like static steps, and you know that the static number is the number of threads divided, or however many strings divided by the number of threads.
Yeah.
That way you make sure they're sequential.
So you make sure that each thread does a sequential part, but in what order will the thread's output get concatenated?
So, but isn't there?
We have no control over that, and it's not going to go and give you the choice. Okay.
So,
So and why didn't you just? So you could do it that way. You could write your own program to do so, but use this formula as such, without any modification. Variations of it can be done, right? You can even have thread numbers, and you can make sure that the first thread is assigned the first chunk, the second thread is assigned the second chunk, and in the end, the reduce step can go and look at the thread numbers, wait for things, and so it can look at the thread number. It can do that, but not this formula will not do it.
What about the opposite of the guidance step in dynamic? So what if you assigned like 2 iterations to the first one and then exponentially more iterations to the next threads, all sequentially assigned though? That would almost guarantee that your 2-string at the end would be the concatenation of all the correct strings in order.
There is no guarantee on in what order the final reduction step will happen.
Isn't the final reduction step done in the order at which the threads
no guarantee.
No?
No guarantee.
Okay.
Okay?
And even then, your first one could take, as much time as every other one combined. There's no guarantees on that. And
Also the way, thread scheduling, no guarantees.
Okay.
Okay? But you can imagine variations of this again. Okay?
So with OpenMP, are we the one, or are we as the coders giving this declaration of this is safe? Or is it able to see the addition and know that this parallelization is safe?
It's just looking at your comment. It doesn't look at your code at all.
Okay, yeah.
Okay? So string is not, so the assumption here is that we are doing some binary operation repeatedly on better values, and that's both commutes and is associative.
So couldn't you do this in parallel, but have a reassembler on the other end of the parallel?
Yeah, that's what I keep talking about. This is the reassembler. But the reassembler can do things in any order it wants to. Okay? And the work can be assigned in any order in general. So
So it can be done.
by you.
But we lose OpenMP to be able to do it. We have to do all of it ourselves.
Then that would just defeat the whole purpose
Yeah.
of
So what it's requiring you to do say is that, look, the operation is going to do in the end. How is it going to compute this value? By applying some operation at the end. That operation better be commuting and better be associative. That's a requirement it has.
So we
It
can't
won't.
use OpenMP at all.
Sorry?
We can't use OpenMP at all, or can we use it for this middle part, and then after OpenMP's stuff is done?
Next slide will tell us how to do it.
We can't use the for aspects of it. The parallel part with thread numbers, thread-aware computation you can do.
we're probably going to mention the keyword used for making so it does this properly soon.
Yeah. So let's go and figure out how we're going to do multi-level reduction. And rather than just going and giving you what OpenMP requires us to give, I'm going to gradually come up with a manual solution first, and we'll see how the manual solution can be automated. Okay? So here's my manual solution. I go and create before the for loop something that the for directive is totally unaware of. I create my replicated variable. Okay? And assign them 0.0. So I do that. I'm making this thread aware just because I'm going to later show you how to make a thread unaware. Okay? And each thread executes this iteration, and it goes and adds not to sum a variable, but to its sum the list. And then after the for, when there's only one thread left, we go and sum up the sums. Okay, that's the algorithm without using any OpenMP new OpenMP constructs, but in fact by going and adding the thread number to our code. Okay, so that's in code now. Okay, and that's a scope issue we were talking about. And now what is the problem that arises with this solution?
You have to change multiple things or to extend it for multiple threads.
You have to change.
Both the number of sums you have and your thread number count.
Right, you have to change that, but any performance issue here that Chris alluded to earlier?
That is false sharing.
You have false sharing in our sums. The sums are all consecutively allocated. Each thread is writing to a sums variable. Okay, so you have false sharing. So even though we are not using OpenMP's for directive, we're trying to do things ourselves, we still haven't quite got it.
What if we make the a sums be pointers to other floats?
Okay, so we can make this a capital float.
Yep.
Okay, if you make it a capital float, we increase overhead a little bit. Okay, and this solution won't work for C. Okay, and also remember we want, if possible, this to be taught as early as in the career as possible. Okay, so
So can we not do that? Can we not use capital F?
So in this current case, it's only limited to 2 threads because of a sums only having 2 elements.
yeah, we've decided
It's
we have
hard
to.
to-
But if we can just make it a constant,
The a sums.
we can make the dimension of this. We can initialize a sums in a little array, in a little loop, And if we have n threads, initialize all of n of them.
Yeah, then you can't
Could
have
you
that,
just make it into a
comment
mutable object? So
Sorry?
instead of something where that you can just append.
But this is 101 programming. You can always go and you can always have n items and initialize them in a loop. Is that you're worried that I can't initialize this particular thing in a constant? Okay. So let's look at Chris's solution. Is it really going to work by making capital float?
Wait, I'm so
See what he's saying?
I don't know what the problem is.
The problem is that floats, the sums are in an array, allocated at adjacent locations.
So it's a critical area, and if you access it, it causes the.
Do you get that part?
Oh.
And they're all writing to it.
And the alternative I came up with is what if you floats, or pointers.
To get that? So Chris's idea is that make the small float a capital float, and it's not going to work. Why not?
float means, I guess floats are immutable.
If floats are immutable. That means each time you add a float, what will you have to do in the sums array?
Create a new one,
And assign a new value to that array.
which is still in critical memory.
Okay? So we need some help. And OpenMP provides us with that help. Okay? We're still going to make it thread aware. So cache issues and allocation over sums. False sharing is all threads write to adjacent array slots. Okay, that's the problem. Okay?
So it'll have that memory issue where there's
Yeah.
stuff.
Okay.
What's the word for that again? I kept saying critical.
The false sharing.
False sharing.
False sharing?
False cache sharing is the more precise term. Okay?
So the cache is the threads cache. Or the cache is the area in real memory.
The CPU cache.
It's per processor. Okay. So here's what OpenMP gives us. Remember when we were converting our code to a Java code, we had to create a context object that was shared by all threads. Okay, if you don't remember, just believe me, we talked about that. Imagine that context variable object being created. So these were the variables that were not going to be in scope of the thread, and we had to go and pass them to the runnable, just as we pass regular objects values to a command object, which Jed mentioned. We'll make those context objects private. In other words, they are not sharing a common object. So if I go and say OMP parallel, we're not using for right now. We're using OMP parallel, not OMP for parallel. We're using OMP parallel, and we say private asum. Okay? Saying that within this particular critical section, within this statement, I'm going to declare a variable called asum. Just one variable I declare. But hey, OpenMP,
Replicate.
you replicate it. Okay? So in our implementation, when we go and create a runnable, we'll have maybe the variable stored in the runnable itself rather than in a common context object. Okay? And then we'll go and do this stuff. Now that we haven't put the parallel in the for, we'll have to do our own division of work. Okay? In process iteration, because we aren't using its for. Okay? And then we'll go and add up the values. Now, before we finish our parallel work, we'll go and add to retval in a critical section my value. So that is going to be at the end of the sum. I'll go and
But we're not using the OMP thread, so why do we need to make that critical?
sorry.
We're not using our.
No. We are using OMP parallel. We are creating multiple threads. We're not using OMP for parallel.
Oh.
So we have to do process iteration.
Oh.
Okay, which goes and says, hey, I'm going to decide how my iterations are divided
Okay.
because I'm not using the for loops.
Did we tell it how many threads to use?
Yes. If we don't, it'll pick up a default number.
Oh.
Okay. So yeah, we didn't. So we didn't have to do that. Now we don't have to worry about 2 versus 4. Okay, that's done. It just picked up a number of threads, and we have a retval variable and we have a sum variable. Retval is before the parallel construct, so that is shared. Okay. In the parallel construct, you can declare a series of variables to be private. Those variables are created are private copies. So that's and we do this. Okay.
That's our critical section.
Sorry.
That's our critical section.
So now is the critical section.
So moving the summation outside of the individual thread loop is what allowed this to happen?
Yes.
if we did make asum private, would asum have been shared between threads?
Yeah.
Okay, so the part that we're allocating to each thread, does it share things like the A list? Sharing A list isn't a problem though?
Why is that a problem? I'm just reading the list.
Yeah, we're not right.
We're not ready.
That's,
Yeah. So can you shut your computer? If you're going to ask questions, I want that shut. Okay, because I saw you just repeated questions that you were that were answered while you were watching your screen. Okay. Okay. Any questions?
Could this is a dumb question, but could you have, instead of having the vehicle section, had sort of a listener writer thread that will read from like sort of like what we do with this one, the buffer thread that will read from all the threads finishing their sums, and then that only one thread can write the summation, the final summation.
Yeah, so you can do all that stuff. In fact, if you do assignment 0, that's kind of what we are doing. Okay.
The previous slide for when we were all sharing on ASUM, which is a array. I didn't see a critical, like a / like be critical there, but it's said to be false sharing. Is it like?
Sorry, say that again. Which is fault sharing?
In the previous slide, like
In the previous slide, we had independent variables. So I can't go back. I don't want to go back to the previous slide. You realize? Okay. Okay.
The reason you use the private asum, if you declare asum outside of the parallel section, so you can find this is taken internally in private. So everything by default is shared.
No, this OMP, the private thing better be a variable that is declared within that attributed statement. In the attributed statement, you should make that only those variables. Okay, so you don't go and refer to variables outside that.
Okay, I thought it was it's things that are outside, so you can set up so it'll keep the value that it had before, and then find whether it's shared between everything or it needs to copy it per thread, and how to handle.
That's true. That is true. But in this case, if you did not make it private, actually the default is private. I'm sorry. Okay, but it doesn't matter what the default is. But you can have this variable be shared also. Okay, in which case you produce. So even though it's within that scope, you'll go and make it shared. So you're right. Previously we were talking of variables outside the scope. Now we're talking of variables inside the scope. And inside the scope you can have shared or private. Yeah.
What scope are we referring to exactly?
The scope of the statement that we have attached our OMP directive with. No, you can't ask questions. Sorry.
I'm on the
It doesn't matter. I don't. You have to shut this down.
I promise no one's asked this question. Does the / private each thread mean anything in OMP?
No, it's just for you guys. Okay. Other questions?
So you said the default's private inside OMP.
I believe so. I mean, these are details that I can't 100% sure, but I believe that.
If we write private and the variable we're making private, is that distinct from not having private?
Yeah, so I'm just being sure here, doubly sure. It's just like putting parentheses in expressions when I'm not sure what the precedence is. Okay, but I believe from what I read. Okay, so we've got now another particular term called private versus shared. That's a big deal people make in OpenMP. And you can have private or non-private variables. Okay. So I haven't really automated things the way I would like to. I mean, I'm doing process iteration, right? So, but I've got a formula, right? I've got a formula. I have a private variable there. I will go and have a for loop in here. We'll do this at the end. So we can we add more parameters for parallel to create this automatically? Okay. So we are doing sum here. We might want to do multiply later. Our for loops are not bound to an array or to multiply or to sum. So how can we go and add some loop parameter that allows us to get rid of process iteration and yet allow generality. So, and to answer that question, let me ask you this question. What if I want to compute rather than the sum, the product?
You replace the operation
Okay, what will change here? I'll go and name the variable sum to.
of product.
I'll initialize it to
Oh,
1.
oh, right.
Okay? So a different value. I will go and have the same thing here. What will I change? A sum plus equal to something with?
Product times
And retval.
times equals a product.
So what loop parameters do I need? So let's go and do that. I did that this morning, I'm not sure, okay? So I did this. So what parameters do I want to add to the for loop now? If you get this, you've got it. You've got the most interesting part of this whole thing.
The starting value for your accumulator and the accumulation operation.
So somewhere the initial value, okay? What else?
Whatever your reduction operation is.
What your reduction operation is. Can I go and get the initial value from the reduction operator?
In these examples, yes.
You know, we can have default values that for sum it is plus it is 0 and for product it is 1. Okay, excellent. So we'll go and say, hey, loop, do the reduction yourself. The operation is plus, and you needed to also mention what variable to sum up all the private values into. So what it's going to do is going to take retval, create a private version of it, right, because it has to know, and then go and use the private values and sum them up in the other retval. No, I'm sorry, you were writing on your board. I'm just not going to entertain more questions from you. Just period. Other questions?
Yes, when you looked up, so I was getting a private and first private mixed up. Where private, it makes a separate value for each one that's not initialized to anything. Whereas first private will take the value that it has before you were in the OpenMP section.
First, so here you're not saying any private here.
Yeah, like on the previous slide, instead of a private you could use a first private rec val, and that'll start at 0 and then add everything.
So what problem are you solving here?
No, it's not solving problems, explaining what I was talking about earlier.
Yeah, you know, I understand the scope issue.
So is the
Reduction. Oh, sorry. I'm sorry. Thank you.
okay?
Reduction.
I just want to make sure, but is that replacing your sort of that
Process iteration.
final adder, that final little piece?
Yes, it's replacing a lot of things. This loop is much shorter.
Since we don't have this slide, I'm trying to figure out what was removed.
So tell us what it's going to do with the retval first. It sees reduction plus retval. What's it going to do with retval?
It's going to add the ret vals from each of the threads together.
Firstly, it's going to create the retvals for each of the threads together. Firstly, it's going to create. It will automatically do the private that we had to do manually last time.
So that was done automatically by what?
But now it's doing it automatically. Before we declared it private.
Okay.
We declared two variables, retval and a sum. Now we're declaring only one variable, retval. It automatically before the loop it will create a retval.
And is this ret val thread specific? This is the private ret.
This retval stands for two things.
Okay.
At the end of the loop, it stands for the final variable.
Yes.
At the beginning of the loop, it stands for the private variable.
Okay.
So it was retval 1, retval 2. And so when you do, inside the loop, it stands for the retval 1 is used, the private variable is used. Outside the loop, the final variable is used. So this particular statement, retval plus equals a list I, is replaced with two statements. So somebody want to describe, yeah, Hunter.
Sorry, I don't have the answer. I have a question. So basically, there's the retval that's declared before we do any of the OMP setup.
Fine, right.
So each retval afterwards inside the for loop is a thread specific retval that somehow still comes out and is returned as a sum.
So what's going to happen? This is equivalent to the previous code. In the previous code, we had to declare a private variable called a sum. and a shared variable called retval. This retval is standing for both. The basic idea is that you just write one thing like this. Okay? And what should happen? Before the for loop, the private variable is created. Now what's happening inside the for loop? When you say retval plus equals a list I, we're still accessing a list I. The plus equal to is being assigned to the private variable, the shared variable.
Private, right? Which is why I'm confused how it gets private to shared.
Okay, so it's assigned to the private variable. Now we have a bunch of retvals. They have to be combined together. We don't have a plus operation to do that. But it knows that you've declared plus there. It can apply the plus value, use all your private variables, combine them together into the final retval.
So the OMP statement is saying you're giving it a final value to save all of those two, and that's what's actually doing that. Yes, I'm right, you're saying.
It's giving you a final variable to save into. It's also giving you a template for a variable that it's going to automatically create. It's doing two things.
So reduction creates it declares creates the private retval, and when it finishes doing each of the things in the two parallel threads, it'll add those two private ones together.
It'll apply the operation you gave there, which happens to be add.
If we put star, it'll multiply it. All right, that makes sense.
Each thread get the value you assign retval in the first place, or does it get based on the operation? So like, if you said retval is 1, suppose you wanted to do 1 plus everything, does the private thread get 1 to initialize to its private variable for everybody?
No, hang on. Where did the 1 come from?
So you said float retval is equal to 0.0, right?
If you give, say, retval equals 1.0.
Yeah. Is that what's used, or does reduction determine what's chosen?
No. So the private variable will be initialized to 0.0.
Okay, because of the reduction.
Because the operation is plus.
Yeah, okay.
But your retval will be originally 1.0. That's fine. And then you'll go and sum up all the other values on top of it. Yeah.
So if we had a non-zero value, like non-1 value, just a random value of retval, that would be applied at the end.
At the end, yeah. But yeah.
But you really do funny stuff if you
You can do lots of funny stuff.
like I was thinking, what
If you go and put retval star equal to here, that's your problem. It's not going to look at the consistency there.
So does the plus after reduction, is it a one operation sort of space, or could you put like a small expression in there?
You can put whatever you want to in that variable, in this expression, in this here.
No, not here. It's still right after reduction where it's plus retval. Can you put?
Yeah. Now we are getting to the really interesting part. Okay. So private variable created before attributed statement entered for reduction variable retval. Okay, this is in slow motion. Initialization of private variable depends on the operation. Okay. So it's initialized with value depending on the reduction operator plus. Okay. All occurrences of reduction variable replaced with private variable in the for loop. Okay. You can have it in any way. It doesn't know it's just doing a replacement. And reduction operator plus repeatedly applied to private variables and resulting reduced value stored in reduction variable. Okay. Okay. If you can do this, guys, we are in really good state. I think very few people in the world understand this. This was invented very recently in OpenMP. But this has really helped crystallize things. Do I still have reducation? No, we don't. I have nothing here. So this is the map reduce problem that people often go and look at. When they do map reduce, they look at word count. When they do OpenMP, they don't do word count. But let's try to do word count in OpenMP. Okay, nobody's done it. My Java implementation doesn't do it, so I don't know whether this is going to be correct or not. So we'll probably find more errors. But let's go and try to get an idea how this might work. So the word count problem is saying, let's go and assume that we have a bunch of words. And I want to have the counts in the end. That the appears 2 times, A appears 2 times, and appears once. Okay, this is a classic sort of data mining problem today. You're given a corpus of text if you want to know how often certain words occur there. Natural language processing could make use of it, all kinds of mining could make use of it. So here's how I could do it. I could have, forget about parallels, let's just do sequentially. I could have word count, take a string of words, and I could create a hash map in the beginning. And for each word, I would go and say, call an add function that says, take the current hash map, take this word, take its occurrence as 1, because it's the first time I've done this, and please update in your map the count for word. Okay, and Ken and Andrew are very quick at looking at code and finding bugs. Please let me know if there's a bug there, and Ken especially. So this, assuming add works the way I said, this is probably work. Now, how could I do this in a reduction fashion? Okay, good. Because
So, maybe not in like this. So you split up like your words array in the dynamic way or however you want to do it. Just leave that up to another thing. So if you're in relation to how you did the previous page, you would create your parallel threads and you'd have a reduction in there instead of having like addition with like your return value or like what is the return value here? The word
it's a map.
Yeah, the map.
So we want to, remember, we want to return a map in the end.
Yes. So you, instead of having the plus symbol, you have the function that takes the map.
Okay.
And it's going to process.
Okay, no, slowly. I'm going to have a binary function. Reduction requires a binary function. So he's fine so far. We want our own function. What will be the argument types of the function? Two maps. Okay. So my add is not written properly.
You'd have to restructure.
I'd have to go and do an add of a map to a map. Okay, so this intuitive thing won't work. And by the way, now we're using integers. We're not using int, and we talked about earlier that means dynamic allocation. Each time I go and update a count, I have to allocate a new integer. Okay, so we run into garbage collection problems. So reducible parallelism, no. Both operands of reducible add should be of the same type, right? So I've got a map plus now. Okay, now we understand this, guys. 7 minutes, I'll be so happy. I've got a map plus that takes a map as an argument and another map as an argument, and it adds up the two maps. Okay, assume that works. Again, Ken will tell me if there's a mistake or not. Okay, and I'm just calling, in fact, my other add. Okay, so just focus on there's a lot to focus here on. But just focus on what I'm talking first. Okay, so you guys get map plus is taking these two adds, and here I'm going and saying I'm creating for each particular word. I create a new hash map. In that hash map is the word plus the number 1, and I'm adding that. I'm doing a map plus on the final value and this new value. Okay? So I'm doing map plus a word count and added value, returning a word count in the end. Just like my previous problem. Except that the add now is an add of maps. Right? Now this is going to work as long as we tell OpenMP all the things that it needs to know. We wrote our add operation. It's not like a plus or a star that OpenMP knows about. Okay? It has to know how to initialize the variable. It has to know what the operation is. So let's go and look one by one. I went and said reduction map add. I didn't say plus. I don't have a map add function here. Okay? And I don't know why OpenMP did it, just to increase flexibility. But somehow this map add has to be mapped to this map plus.
Why did you say map plus then?
It allows this flexibility.
Oh.
So I'm showing you the flexibility.
Oh,
okay? It may have to do with operators that you might want to give names to operators. To the plus operator you might,
aliases.
or yes, something. So I don't have, this is like a very new thing. You won't find examples of this, very many examples. Yeah.
So at the top, the second.
Yeah, we'll just go gradually. Okay?
It's not like that's explicitly do it, so you can't accidentally use like the wrong thing. So you have to declare this exists, and I want to use this for reductions. So you can't say something else that was taken.
No, the thing is that it does need, and as Hunter was pointing out, that we have specified something there, but it does require, it allows you to have the flexibility, because I guess it doesn't want to read the name of the method there. So in Map Plus, now we have not only annotations with statements, for statements, but also with methods. Okay? And in this thing, I go and say, look, I'm declaring something that will be useful for reduction in a for loop later. Okay? So I'm saying, I'm declaring something called map add, which can be used in a for loop reduction. And I'm associating it with this map plus. So, just call this function. Okay, so this map add and this map plus are corresponding. Okay? I am declaring the type here. Okay, remember we have to have, that plus was working on any number. We have to go and say what map add works on. It's working on a map. I'm giving you the map exact thing. Again, please check for syntax errors. This is all I've invented in Java. I've been using in Java. There was nothing to check this stuff. Okay, so this must be the same type as this. It should be, but if it's not, it's your problem. Okay, this should be the same type of the added value. Okay, because if that will be the case, if map plus is taking these arguments, it will be the same type, and it should be of the same type as the return value, the word count. Okay, and what is this saying? You think? It's saying when you go and create your variables, which you will, okay, because we've already said a word count is the variable there, we'll create a mirror of that copy. Please execute this statement to initialize it. So this is now all formalizing the stuff that I talked about earlier. Okay? Before the loop private initialization. And what do you think this OMP out and OMP in are saying? So at the end of the loop, it's got to go and call map plus, right?
It's going to get the output of the OMP thread and
so
the input with one of the inputs.
So it has to know. It has to go and use map plus to reduce all the private variables into the final variable. It has to go and give one of them as an argument, each of them as an argument to the map plus. It has to know in what order to give the two arguments. Right? It doesn't know whether the deft argument is the final variable, whether you're doing add a map to an addition or add an addition to a map. It doesn't know what you're doing.
Oh, that's different, yeah.
So it is saying, I know what the output variable is. Output variable is the variable that is the final variable that I will give you the output to. So whatever you tell me is the position of the output variable, if the first is the position, then I will go and put my output variable in the first position. If output variable occurs in the second position, then I'll put it in the second position. Okay, and output in OMP in will be the other position. Okay, so out is this particular variable, and in is the added value. Okay. So after for loop, second level reduction comes out, the final reduction, by calling map plus with the shared variable being passed in the position of OMP out and private variable being called in position of OMP. Okay, these are user defined reductions. Okay, and you get this, you get the essence of OpenMP. Pretty powerful, and it formalizes what we do. See, what I like about this is we can do all this stuff using our thread knowledge, but we don't know how to use our threads. We don't know in what ways it can be used. So, so just as we had in 401 design patterns for using objects, we kind of have design patterns for using concurrency here. Okay. And just to complete this, this is the syntax there, that you have something called an initialization expression, which is before the loop private variable is assigned. You have operation name there, that is the operation to be used for the for attribute set. the method that you refer to there is the method to be called. And so I'm just giving you the general syntax here. That was by example, this is by this. Okay? Okay, so now I have got reduction completely described. Okay? And we'll start from here next time. Okay, so we looked last time at the concept of reduction, and the whole idea of reduction is divide and conquer. And if you've done divide and conquer questions before, you know the idea is to make your job a little easier to program, to make sure that you can prove things correctly. And as it turns out, in parallel computing, divide and conquer means that the divided work can be done in parallel often. Okay? And that's what we saw with the plus operator, that if you're asked to add up 4 numbers, you can divide that problem into adding up 2 numbers each, and that can be done in parallel, and then you can go and add up the results of the first step. Okay, and we can change the plus to multiply. Okay, and that will still allow us to do divide and conquer. And these are well-defined number problems, and we can imagine also defining our own operations that can allow divide and conquer. So we did that with maps. That we defined a map plus operation that we could do in parallel. Okay, yeah.
Just a quick question. Are these slides on your website? Or
They will be always on my website. They are not today on my website.
not yet?
Yes.
Okay.
That's always the case.
I just don't want to look futile.
Yeah. Okay, I'm working till the last minute on slides. Okay. Andrew's here. Good. So, okay, so there's a notion of partial reduction. We're doing it in 2 steps in OpenMP, where the loop is first reduced by multiple threads partially, and then the main thread goes and does a final reduction. Okay, so that's the general formula. And that ended our discussion of OpenMP, and we saw attributes we could have for general statements, and then we saw attributes we could have for for statements. Okay, and this reduction was in the context of fors. Okay, that we could go from plus to multiply to map plus using similar loops, and we just explained at the head of the loop, which operation we are reducing, and the reduction happened automatically. So that was great, right? And these are general OpenMP statement attributes. And one of these is, of course, the number of threads. So we discussed this a little bit last time, but the question is, how do you choose this value? And that raises the question of, so how to create these threads, and also what the default values for all of these should be. Okay, so number of threads, what should be the default value that OpenMP can use without knowing sorry? 2 was what I showed because I wanted to keep my slides simple.
1 minimum.
Yeah, shouldn't default be
1 minimum, that's the thread that was, yeah. But what do you want to go for?
as many as is safe?
As many as is safe, but if your application works, 2, 3, 4, 5, all will work.
Can we say the question again?
Sorry?
What's the question again?
How many threads should you have? Should you have, if you have a choice, and how many threads should the system use without knowing anything about your application? Sorry? So if you want, as long as your computation is safe, you might just want the number of processors, and you can go and do something like this in Java. You can figure out how many processors you have. Okay? So that's the default value, unless you know better. Okay, and we'll see. We're going to play around with this issue soon. Schedule, do you want static, dynamic, guided? Which do you want? And there's no real science here, but I just want you guys to think. If you had to design something, what would you choose?
I want to say guided, but I feel like that's too complicated with default. I feel like static would just
So that's the thing. Too complicated for for default. I mean, if you're doing some round, all the problems we've seen, they had fixed cost.
Shouldn't shouldn't, I forget the word, shouldn't what you do like, unless you say otherwise, just be static? And if you want it dynamic, you should.
So we'll try to do the most efficient case first, because if all iterations are the same cost, this is the most efficient. Okay, this keeps make sure that we are not in overlapping cache lines and so forth. Okay, step size. So one would keep it very next to each other. So if you're changing, so again, or the maximum possible, right? Which is the number of iterations divided by number of threads. Assuming we don't have very large amount of data that is spread out, that will not fit, fit in memory. Okay, it will require a lot of. Okay, so in static case, the step size is number of iterations divided by number of threads. Okay, and in dynamic guided, it's 1. Okay, so if you're going dynamic, let's go fully dynamic. And I believe this is the case. The defaults. Who knows really? Okay, but I believe that's the case.